So good morning, everybody. My name is Sylvain Cordier. I'm a PhD candidate at the University of Sherbrooke in Canada. So I will tell you about the dynamic LCA of an increasing use of wood in the buildings and its consequences, mainly related to material substitution and CO2 sequestration. So in the next slide, I just present you an overview of what I will tell you about. So, and in the next slide, some word about the context. So, as part of a policy for the use of wood in construction to support forestry and construction industry, the government in Quebec provides a roadmap to increase the use of wood in construction. So we see more and more buildings with more than 6 floors sometimes, with a solid wood structure. So with this increased number of public and also with an increased number of publications that show that the use of wood in construction may be an eco-friendly option. So decision maker may move to use it on a large scale. However, the environmental benefits of some project, they are not easy to extrapolate. So making the decision for large scale use of wood in construction can have consequences that extend beyond the boundaries of the sector. So better understanding of the consequences would help the decision making. In the next slide, some facts regarding the literature review. The static approach used to do not consider the temporary sequestration of carbon by wood projects. Also, climate change benefit should also be assessed from a consequential perspective because of this scale effect, and also there can be pressure on other materials and on the resources. And finally, temporary carbon storage does not always result in a climate change benefit, as the benefit disappear on an infinite time basis. So carbon storage may be temporary during the building lifetime, but at the scale of a growing stock, the overall storage depends also on the lifetime of the stock. So what can be the main contributor between material substitution, carbon sequestration, and end-of-life sequestration? So first, in the next slide, we have to estimate the amount of wood that can be used in the non-residential structure. Why non-residential structure? Because in Quebec, the residential building is made of wood for around 90% of residential buildings, and for non-residential building, the market share is around 30%. So there is a potential increase for wood in the non-residential market. Next, so we had to estimate how much steel and concrete are substituted per ton of added wood in the structure. Also, there was the modeling of trees that grow up after the harvesting. And finally, we had to model the dynamic stock to help the stock to renew and to reach its end of life. And finally, the EcoInvent 2.6 helped to model the background LCA, and the DINCO tool from Levasseur help us to make the impact assessment. So in the next slide, a few words about the production phase. Thanks to different case studies, we were able to have an estimation of how many steel and concrete can be substituted if we add 1 ton of wood. So we had 3 scenarios. I will only focus on on the minimum scenario and on the average scenario. And for each scenario, we use different type of steel and concrete. So for the minimum scenario, even if the result is just above the x-axis, there is no impact displacement in the production stage. So it means that wood does not sufficiently replace steel and concrete, which are not GHG intensive compared to the average scenario. So this minimum scenario is more relevant to understand the contribution of the other element of the modeling. So I presented you the production. So in the next slide, we have the modeling of temporal carbon sequestration depending on the end of life. And also in the next slide, we have the tree that grow for 100 years. So for the end of life scenarios, in Quebec, the government is pushing to ban the landfill of organic products. So any recycling or energy recovery scenario cannot avoid landfill. Also, another activity that cannot be avoided is the harvesting of virgin wood for cogeneration production or particle board, because virgin wood that feed those industries is constrained because it is a specific virgin wood that cannot feed the sawmill production due to its non-conformity for lumbers. So the first end-of-life scenario is the following. The structure is shredded and burned for cogeneration and heat of electricity, and the recovered electricity avoid the production of wind turbines that are forecasted in the roadmap. The second scenario that you see in the middle, it also guarantee electrical supply to guarantee electrical supply. There are also biomass cogeneration plants that incorporate backup boiler of equivalent capacity and one with natural gas. So in the second end of life scenario, there is the avoidance of natural gas, and in the last end of life scenario, it is the recycling of the structures to make particle board. So in this case, there is no biogenic emission at the end of life. So now I will present the result, and for each end of life scenario, we'll present the first case. I will present first the case where the substitution of steel and concrete is not enough. So in this case, we will see which end of life scenario make the result negative or make a benefit. No, please come. Yeah, so first, for this end of life scenario, only avoiding the production of wind turbine is not enough in a very long term for two reasons. First, you see that the yellow curve related to the end of life is positive. And secondly, because the carbon sequestration in green and the biogenic emission in blue will cancel each other on an infinite time basis. So in the next slide, for the second scenario, in case of natural gas avoidance, the result is negative mainly because of the avoided emission of the natural gas. And finally, in the next slide, for the production of particle board, even if the yellow curve is positive, as long as we keep the carbon store in product, we can keep changes to have a benefit. So the next slide summarizes the three end-of-life scenarios for material substitution of steel and concrete that is not enough. So then, in the next slide, in the average scenario of material substitution, it is the material substitution that contributes the most to the result. So until now, I presented result with constant greenhouse gas intensities for steel and concrete. So since technologies are likely to improve in the future, in the next slide, I present figures with sensitivity analysis on the GHG intensity of steel ingot and cement production in 2030 and 50. So based on roadmaps and other references, we consider a GHG reduction of 25% and 38% for cement production, and reduction of 30% and 60% for steel ingot production. So still here we can see that so far there was no significant change in the interpretation of the three end-of-life scenarios for both substitution scenarios. And in the next slide, expected for the please come back. Expected for the minimum substitution scenario with cogeneration replacing only electricity. It shows just an earlier impact on the climate change that the same scenario with constant greenhouse gas intensity. So for the other five scenarios, the avoided impact was lower with decreasing GHG intensity than with constant intensity, but the conclusion did not change it. So in the next slide, I would like to say some word about the dynamic assessment. So here it is the scenario for which there is less benefit in increasing the use of wood in the non-residential structure, and the black curve is the total dynamic assessment. So in the next slide, we can see that the static result give opposite conclusion because it is not able to consider the time gap between the biogenic carbon sequestration and the biogenic release. So it is for a temporal horizon of 100 years. And if we go further in the next slide for a temporal horizon of 500 years, for further temporal horizon, the static and dynamic assessment give the same conclusion, even if the static assessment will overestimate the result. And finally, in the last slide, it is the same case. In the next slide, please. So yeah, in this case, when the substitution of steel and concrete is the main driver, we have like in the previous slide, the static is just above, just overestimate a bit the final result. So to conclude, the substitution of steel and concrete is the main driver to the benefit, and the carbon sequestration also allows for a benefit, but for the first years and depending on the end-of-life scenarios. And the static approach overestimate the impact on climate change. And finally, with a dynamic life cycle inventory that contains emission sequestration avoidance that do not occur at the same time, the static approach can lead to opposite conclusion to the dynamic approach. So in the next slide, I would just like to thank the financial support of Natural Science and Engineering Research Council of Canada and the industrial partner of CERCEL. And thank you for your attention.